Hello, listeners. Welcome to the Stainless Steel World podcast. My name is Joanne McIntyre. I'm the editor-in-chief of Stainless Steel World. And today I'm having a conversation with Dr. Elin Westin from voestalpine Böhler Welding. Elin is a qualified welding engineer and within voestalpine is the specialist for global R&D on joining corded wires. So welcome, Erin.
Thanks, Joanne. It's a pleasure to be here today.
Now, Elin, the reason I'm talking to you is that at the recent Duplex World Conference, which took place in Rotterdam in May 2026, you presented a really interesting and extensive research paper titled Enhancing Microstructural Analysis, Best Practices for Preparing Duplex Stainless Steel Weld and Additive Manufacturing Deposits.
Yes, this paper was published online in Welding in the World earlier this year. And this conference was a great opportunity to reveal this paper for a larger duplex community.
Right. So if we go back to the beginning, how was the idea for this research actually born right at the start?
Well, I started working with duplex some 20 years ago. And at that point, I was surrounded by several experts on duplex preparation and metallurgy. And with time, I realized that this is a luxury that most people don't have today. So I think about 7 years ago, I contacted my former colleague, Jon Jonsson at Outokumpu Stainless, and I asked if he would like to contribute to a paper of this kind. And before we finished the paper last year, we also involved some duplex friends working at the University of Twente in Holland and Ohio State University in the US, and they contributed with some beautiful images and experience as well.
Right. What a great collaboration. Now, Elin, you have very generously decided to make this research paper publicly available, which is why we're discussing it today. And in fact, we've already posted it on the Stainless Steel World website where anyone can read and download it. So why did you decide to make it available to anyone at no cost?
The prime goal at all with this type of work was to help young professionals so that they can excel earlier in their careers and avoid having problems with preparation, which can delay their dissertations. But also our customers and the metallurgic laboratories that they subcontract to, they are struggling sometimes to interpret the micrographs. And in worst case, this can lead to project delays and even financial penalties. So it was actually my company who suggested to pay for this open access to make it publicly available.
Now, Elin, there's already been extensive R&D done on weldability challenges with duplex stainless steels, and much of this is applicable to additive manufacturing. So what prompted you to delve even deeper into this topic?
Well, I have the pleasure to review many papers on both welding and additive manufacturing of duplex stainless steels. And unfortunately, I had to reject some of these papers due to either poor image quality, but sometimes the authors have even drawn their own conclusions based on these images.
Mm-hmm.
Additive manufacturing also adds another layer of complexity. We have repeated reheating and complex thermal cycles. And this can expose material then multiple times to critical temperature ranges where, for instance, a sigma phase can form. And at the same time, we see a growing interest, a lot of publications on additive manufacturing. And we there see that there is a need for accurate and reliable sample preparation. And compared to conventional welding, the heat flow and cooling conditions are so different that we have much greater variations in microstructure throughout the built component. Additive manufacturing processes with wires, they build components layer by layer, and they are subjecting previously deposited metal to repeated thermal cycling and prolonged reheating. And the heat dissipation is modified as compared to traditional welding, and thereby generate larger variations in microstructure in the buildup than in traditional welds.
Elin, tell me about some of the key findings that you've presented in this paper.
We have created different best practices for preparing samples to effectively reveal the microstructures and also secondary phases in duplexes. And we have tried to find a wider range for phase measurements. We present a wide range of preparation, starting from phase measurements, but also going to investigation of individual particles in detail. And we want to provide alternatives depending what is available. There could be special instruments and chemicals. And of course, safety is very important in laboratories where students work. So sometimes there are alternatives presented if nothing else is available. Even for experienced metallurgists, I believe that the paper offers some insight that can be new and also useful.
So, Elin, as many of our listeners already know, the name duplex is derived from the fact that the metal has more or less equal amounts of ferrite and austenite to optimize both mechanical properties and corrosion performance. So, how does welding and also the DED additive manufacturing process affect this critical balance?
Welding alters the microstructure and phase balance in the weld and the heat affected zone as compared to the base material. And the ferrite content is influenced by several factors, such as the composition, the filler metal composition, if used, and the type of shielding gas that is applied. Also, the heat input and the interpass temperature will affect the dilution level from the base material and also the cooling rate, which in turn then determine the phase proportions.
Okay, so what's the result then of having too high ferrite or austenite following the welding process?
Well, if the ferrite is too high, it can affect the impact toughness negatively, reduce the pitting resistance, and in worst case, there can also be hydrogen embrittlement, although I would say that this is quite unusual in real life. But we see lower impacts and corrosion properties, and I would say that this would be one of the most common reasons for having corrosion issues in practice. If the austenite is too high, mostly this is rarely an issue, but there could be reduced strength and also stress corrosion resistance. But if I would have to choose, I would prefer to go higher on austenite than to go higher on ferrite.
Right, that's clear. Now, your paper gives quite detailed explanations of best practices to achieve accurate microstructural characterization. We're also able to identify some pitfalls that future researchers should look out for.
Yes, we try to highlight several typical pitfalls. These include preparation artifacts caused by actually the operator polishing could use too much force, or there could be insufficient amount of lubrication. But there are also some different etching effects that can be misleading. We have some metallographic surprises, such as partially molten particles, which quite often are mistaken for intermetallic phases. And we then show a number of examples with images to help the readers recognize these features early and to distinguish them from actual microstructural phases. We also provide some practical guidelines how to differentiate between them. So if you think that this is that, please do like this.
Okay, that's, I'm sure, really useful for researchers in the future. And how do you think that your work will be used in future to further research microstructural analysis for welding and additive manufacturing?
Well, we have structured the data so it supports further analysis using a range of techniques, from light optical microscopy to more advanced methods such as SEM, EBSD, and TEM. And our aim was to make it easier for users to choose the right method based on the equipment they have available and to understand when they would need more advanced techniques. Ultimately, this should save time for students and improve the quality of published micrographs and also support more experienced professionals who are new to duplex materials.
Elin, this work aims to establish systematic best practices for the characterization of duplex. What are some of the key recommendations that have emerged from this research?
One important recommendation is not to overlook optical microscopy. Many metallurgists go straight to advanced techniques like the SEM or EBSD, but a simple optical microscope can already provide a great detail of useful information and with much easier preparation. I would always recommend starting there, at least to confirm that the sample is free from scratches, cracks, or even drying stains. We also show how different preparation and etching methods reveal different features. For a complete characterization, it's often necessary to use more than one method. So, for example, the commonly used Böhler 2 etchants can conceal chromium nitrides, and these are then better revealed using oxalic acid. And if sigma phase is present, sodium hydroxide etching or backscatter SEM imaging can be much more effective than the Böhler. And in more special cases, detail analysis may require TM, and the paper outlines some basic preparation approaches for those situations as well.
Great. Now, lots of really useful information in there, Elin, for current and future researchers and students. Thank you for joining us today. We've made your paper available online. I encourage all of our listeners to read and download it.
Thank you, Joanne, for making the paper available to such a wide audience. I really hope that it can be a useful resource for researchers going forward.
Thanks again, Elin. To our listeners, we've included the webpage where you can find the research paper on the opening slide of this podcast. I know a lot of you will be very interested to go and have a look and download it. Thanks again, Elin, and thanks for our listeners for listening to the Stainless Steel World podcast.